So in this video, we're going to be going over some more RS configuration practice problems. So here we have our first example, and we have this molecule over here. So our first step is to first identify all of the atoms that are chiral centers. So let's start with this atom over here. This bromine atom has 3 lone pairs, 1, 2, and 3. Now, like I said in the previous video, lone pairs do not count as substituents, unless you're talking about pyramidal inversion. That's an exception, but we're not going to get to that in this video. That's a significantly different topic from what we're going to be covering here. So, therefore, since these lone pairs don't count as substituents, this bromine atom doesn't even have 4 substituents. And in order to have a center that's chiral, you have to have 4 different substituents. Therefore, this cannot be a center that's chiral. Let's look at this atom over here. So this carbon atom is bonded to this bromine atom, and it's bonded to all this. So it's got 2 different substituents. However, its remaining 2 substituents are hydrogen atoms, because you have an H over here and an H over here. Now, these 2 hydrogen atoms, they are equivalent. Therefore, 2 out of the 4 substituents that are bonded to this carbon atom, they're the same. And those substituents are these 2 equivalent hydrogen atoms. Therefore, this carbon atom is not bonded to 4 different things, and therefore, this center cannot be chiral. It is achiral. Now let's go over here. So here we have this carbon atom, and it's bonded to all of this. It's bonded to the CH2Br group. It's bonded to all of this. However, its 2 other substituents are once again H and H. Therefore, 2 out of its 4 substituents are equivalent, and therefore this carbon atom also cannot be chiral. It is achiral. So we have that so far. Now let's go to this atom over here. Now this carbon atom over here, it's bonded to 4 different things. It's bonded to this, that's one substituent. It's bonded to this hydrogen atom, that's another substituent. And it's also bonded to this substituent and to this substituent. Now, don't get confused because we have a cyclic molecule. Now, in order to determine whether or not you have different substituents in a cyclic molecule, look at one side and compare it to the other side. When we go on this side, we run into a CH2 group, and then we run into a CO group. When we go on this side, we also run into a CH2 group, but we run into an OH and an H, which is different from this over here. Therefore, we have 4 different substituents, because this is one substituent, this is another substituent, this is another substituent, and this is another substituent. Okay, now if we had a C double bond O group here, if we had a carbonyl atom, then this side would be the same thing as this side, and therefore we would have a cyclic molecule that's symmetrical. And if you have a cyclic molecule that's symmetrical, therefore this substituent and this substituent are the same, and in that case, this carbon atom would not be a center that's chiral. It would be achiral. But because we do not have a symmetrical cyclic molecule, and because we have this side that's different from this side, therefore we have 4 different substituents, we have 4 different things bonded to this carbon atom, and therefore this carbon atom is a center that's chiral. Okay, so we can mark it with an asterisk like so. Now let's go to these carbon atoms. Well, this carbon atom is bonded to 2 H's, as is this one. And remember, these 2 H's are equivalent and these 2 H's are equivalent. Therefore, these carbon atoms cannot be bonded to 4 different things, and therefore they are achiral centers. They are not chiral. This carbon atom, it's bonded to a C double bond O group. And remember, a center that's chiral has to have 4 different things bonded to it. In order for a chiral center to have 4 different things bonded to it, it has to have 4 single bonds directly attached to it. Let's say this carbon atom over here, it's a center that's chiral. It's got A1, A2, A3, A4. And these are just 4 arbitrary things. They're 4 arbitrary substituents, but they're all different, okay? Now, if we had a double bond instead, like let's say we had a double bond connected to A2, remember, carbon likes to have 4 bonds. So, 1 bond, 2 bonds, 3 bonds, 4 bonds. Therefore, it would only have a maximum of 3 different substituents. It would not have 4 substituents, okay? Therefore, if you have a double bond, Or if you have a triple bond also, you cannot have 4 different substituents, and therefore you cannot have a center that's chiral. So this is an achiral center. It is not a center that's chiral. Now let's look at this carbon atom. Again, it's bonded to 2 hydrogen atoms, CH2, and since these 2 hydrogen atoms are equivalent, then this center also cannot be chiral. Now let's look at this carbon atom over here. Well, this is one substituent, this hydroxy group. This H atom is another substituent. And let's look at the third and fourth substituents. Are they equivalent or are they different? Let's go on this side. On this side, you run into a CH2 group followed by a C double bond O group. When you go on this side, you run into a CH2 group, just like here. However, you run into all of this stuff over here, okay? So therefore, when you go on this side is different from this side. Therefore, this substituent is different from this substituent. As a result, you have 4 different substituents, 4 different things bonded to this carbon atom, and therefore, this carbon atom is also a center that's chiral. So now we've identified all of our chiral centers, and we have a total of 2 in this molecule. We have 2 stereocenters, we have 2 stereogenic carbon atoms. So now let's determine whether these chiral centers are R or S. So let's start with this one over here. So remember, when we're determining R or S chirality, what we do is we use the priority rules, okay? And the way I taught you guys to use the priority rules is to assign priorities 1 to 4 to each substituent, with 4 being the lowest priority and 1 being the highest priority. And the higher the atomic number of a particular substituent, this means that the priority is higher. Now, hydrogen has an atomic number of 1. 1 is the lowest possible atomic number, and therefore, in this case, the hydrogen atom has the lowest priority, which is once again 4. And just as a reminder, when you're trying to determine priority, first focus on assigning priorities 1 and 4. Focus on assigning the highest and lowest possible priorities. Once you have 1 and 4 assigned, then you can worry about assigning 2 and 3. It's a bit simpler that way. So now let's try to assign priority 1. Here we have our carbon atom. Let's go 1 atom away, okay? Because, again, with the priority rules, you focus on the point of first difference. So now, 1 atom away from the chiral center, you run into carbon. You run into carbon, and you run into carbon. So we don't have any differences yet, right? So now we gotta go 2 carbon atoms away. 1, 2, 1, 2, 1, 2. When you go 2 atoms away, you run into a carbon atom here, and you run into a carbon atom here, and you run into a carbon atom here. So still no difference yet. Now let's look at what these carbon atoms are bonded to. This carbon atom is bonded to a bromine group. This carbon atom is bonded to an H and an OH. And this carbon atom is bonded to an oxygen, but it's bonded to an oxygen via a double bond. Now, when you're looking at the priority rules, when you have a double bond, it basically means the same thing as this. If you have a double bond and you're looking at the priority rules, it's kind of like this carbon is bonded to 2 different it's bonded to 2 oxygen atoms. You can imagine it that way. But in this case, that fact isn't going to be too relevant when you're looking at the priority rules, because this carbon atom is bonded to this bromine atom, and bromine has an atomic number that's greater than oxygen. So therefore, since this carbon atom is bonded to an atom with a higher atomic number, this substituent has greater priority than these substituents over here. So therefore, this substituent is going to have the highest possible priority of 1. Okay, so now let's focus on assigning priorities 2 and 3. So again, we're at these carbon atoms because we're 2 atoms away from our chiral center. 1, 2. So this carbon atom is bonded to a it's bonded to an oxygen via a double bond, and this carbon atom is bonded to just an oxygen via a single bond. Now, this is where our double bond comes in handy. Like I said before, when you're looking at the priority rules, a double bond can be interpreted as 2 single bonds. So you can imagine that this carbon atom being bonded to an oxygen via this double bond, it's the same thing as this carbon atom being bonded to 2 oxygen atoms via 2 separate single bonds. Okay? So, OH, OH. You can imagine it that way. You can think of it that way. That's how the priority rules work. So this carbon atom, it's bonded to 2 oxygen atoms, while this carbon atom is only bonded to 1 oxygen atom and a hydrogen atom. Now, oxygen here and oxygen here, they're the same element. They have the same atomic number, right? However, here this carbon atom is bonded to 2 oxygens, while this carbon atom is only bonded to 1 oxygen. Therefore, since this carbon atom is bonded to more oxygen atoms, this carbon atom wins out, and therefore this substituent has a higher priority than this substituent. So this substituent is going to have priority 2, while this substituent over here is going to have priority 3, okay? Now, just to warn you, this is not actually how the molecule is. This is just how you can imagine the molecule with the priority rules. In reality, we do have a C double bond O group, but when you're assigning priority, you can imagine this C double bond O group as just being 2 single bonds. And in these 2 single bonds, a carbon is attached to oxygen. That's how you can think of it that way only when you're assigning priority, but in reality, this is a C double bond O group. Now, we have our priorities assigned. We have priorities 1 through 4 assigned. So now we're going to use our right-hand rule. And the way we use the right-hand rule is we use our right thumb and we stick it in the direction of the lowest priority substituent. In this case, that's going to be the hydrogen atom. So the hydrogen atom, it's attached to a dashed line. Therefore, since it's a dashed line, we point our right thumb into the page. Point our right thumb into the page. Now we point the fingers of our right hand in the direction of the highest priority substituent. So it's a little hard because of the orientation, but I'm pointing my thumb into the page. I'm trying to stick my fingers in the direction of substituent 1, okay? So it's like you point your fingers here, you stick your fingers in the direction of 1, kind of like that, okay? You guys should try it out yourselves as well so that this makes sense. Next, you curl your fingers, curl them, curl them, curl them, curl them, okay? As you're curling them, focus on 1, 2, and 3. Now, in this case, as I curl my fingers, I'm curling them from 1 to 2 to 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. This is the natural order of counting because when we count 1, 2, and 3, we go 1, 2, and 3. It's the natural order of counting. And since we have the natural order of counting, this chiral center is going to be R, okay? And just as a reminder, when you're counting 1, 2, and 3, you don't count 4 because you only use 4 when you're determining what direction to point your thumb in. Are you pointing it out of the page or are you pointing it into the page? And in this case, we're pointing our thumb into the page. Now let's focus on this chiral center over here. So right here, we've got to determine our highest priority. Let's go 1 atom away. Well, we've got to determine our highest and our lowest priorities. In this case, our lowest priority is also going to be the hydrogen atom because it's got the atomic number of 1, and the atomic number of 1 is the lowest possible atomic number, so we assign this as priority 4. So now that we've assigned our lowest priority of 4, next let's assign our highest priority of 1. So here we have our chiral center. Let's go 1 atom away. 1 atom away here, carbon. 1 atom away here, carbon. 1 atom away here, oxygen. Oxygen has a higher atomic number than carbon, and therefore this substituent is going to have a higher priority than these 2 substituents, which implies that this substituent has the priority of 1. So now we've got to assign priorities 2 and 3. So now we're going to go like this. We're going to go on this side and we're going to go on this side and we're going to compare the differences. So when we go on this side, we run into a CH2 and then the C double bond O group. On this side, we run into a CH2 group and we run into all this, okay? So this is where point of first difference comes in handy. So in this carbon atom, it's bonded to an oxygen via 2 double bonds. Like we said before, when you're determining priority, it's like, you can imagine it this way. When you're looking at the priority rules and assigning priority, it's as if this carbon is bonded to 2 oxygens via single bonds. Now, let's look at this carbon over here. This carbon over here, it's bonded to a carbon and a hydrogen, okay? And remember, we're 2 atoms away from our center that's chiral. 1, 2, 1, 2. So we're comparing these 2 carbons. This carbon is bonded to 2 oxygen atoms, while this carbon is just bonded to a hydrogen atom and a carbon atom. This is where the point of first difference really comes in handy. This is bonded to an atom that has a higher atomic number than carbon and hydrogen. And therefore, this substituent over here is going to have a higher priority than this substituent over here. So this means we assign this substituent priority 2 and this substituent priority 3. Okay, so now we've assigned our priorities 1 through 4, and now comes the time to use our right hand again. So we have our thumb, and in this case hydrogen is still pointing into the page, so we're going to point it into the page. I'm going to point my fingers in the direction of priority 1, kind of like this, okay? And next I'm going to curl my fingers. So I'm curling, I'm curling, I'm curling, I'm curling. So as I'm curling, remember, I don't worry about 4, because 4, you only use it when you're determining what direction to point your right thumb in. As I'm curling, I only care about 1, 2, and 3. So as I'm curling my fingers, I go from 1 to 3 to 2, 1, 3, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2. 1, 3, 2 is not the natural order of counting. You normally don't count numbers that way. You're going from 1 to 3 to 2. So therefore, since this is not the natural order of counting, this chiral center is going to be S, okay? So we have an R chiral center and we have an S chiral center. So now let's go to our second example. And again, we have to identify all of the centers that are chiral. So for this nitrogen atom has a lone pair. And remember, lone pairs don't count as substituents unless we're looking at pyramidal inversion. But in this case, we're not looking at pyramidal inversion. Therefore, this lone pair does not count as a substituent, so therefore, this atom cannot be a center that's chiral. Let's look at this carbon atom over here. This carbon atom has a single bond, but it has a double bond. Since it has a double bond, just like I explained previously, it cannot be a center that's chiral, because if you want to have a center that's chiral, it's got to be bonded to 4 different things via 4 single bonds that are directly attached to your chiral center. 4 different single bonds, okay? That's how it's got to be. 4 single bonds directly attached to it. In this case, you have a single bond, and a double bond. So this center is also achiral. Let's look at this carbon atom over here. Again, you have a double bond, therefore it cannot be a center that's chiral. This carbon atom, it's got a CH2 group. Therefore, 2 out of its 4 substituents are equivalent, and in order to have a center that's chiral, you have to have 4 different substituents. Therefore, this center cannot be chiral. You have an oxygen atom over here. It's got 2 lone pairs, and remember, lone pairs don't count as substituents, so this atom cannot be a center that's chiral. You have this carbon atom over here. Again, you have a double bond. Therefore, this center cannot be chiral. You have a carbon atom over here. It's bonded to 2 equivalent hydrogens. Therefore, it also cannot be a center that's chiral because 2 out of its 4 substituents are the exact same thing. Now let's go over this atom. This atom is bonded to 4 different things because it's bonded to a hydrogen atom, it's bonded to a deuterium atom, which is just the 2H isotope of hydrogen. So normally hydrogen is 1H, right? Deuterium just has a different isotope. And therefore, since deuterium is 2H, deuterium has a higher atomic number than hydrogen, which means that deuterium is going to have a higher priority than hydrogen. But we're going to get to that in just a little bit. Now, so far for this carbon atom, we've already identified 2 different substituents. This third substituent is different from this substituent over here because you go on this side is different from this side, clearly speaking. Okay, so therefore we have 4 different substituents, 4 different things bonded to this carbon atom. Therefore, this carbon atom is a center that's chiral. So now we assign priority. Hydrogen has the lowest possible atomic number of 1. Therefore, hydrogen is going to have the lowest possible priority of 4. Now, let's assign priority 1. Now let's go 1 atom away. You run into deuterium, you run into oxygen, and you run into carbon. Oxygen has a higher atomic number than carbon. And it also has a higher atomic number than deuterium because oxygen has a higher atomic number because oxygen has an atomic number of 8 while carbon has an atomic number of 6 while deuterium has an atomic number of 2. So since oxygen has the highest atomic number compared to carbon and deuterium, it's going to have the highest possible priority of 1. Now let's worry about assigning priorities 2 and 3. So here we have carbon, here we have deuterium. Carbon has a higher atomic number than deuterium because carbon has an atomic number of 6 while deuterium has an atomic number of 2. So therefore, this substituent has priority 2, sorry about that, priority 2, while this substituent has priority 3. Okay, so we've assigned priorities 1 through 4, and now we point our sum, our right sum, in the direction of the lowest priority substituent, which is hydrogen in this case, so it's pointing out of the page. Now we point our fingers of our right hand in the direction of 1, just like so, and then we curl. And as we curl again, don't worry about priority 4, because you only use priority 4 to determine the direction of your right sum. Now we only care about 1, 2, and 3. So as I curl my fingers, I go from 1 to 3 to 2, 1 to 3 to 2, like so. 1, 3, 2, 1, 3, 2, 1, 3, 2. This is not the natural order of counting. Therefore, since we do not have the natural order of counting, this chiral center will be S. Okay, so these are the two examples that I just wanted to cover for this video. Thank you guys for watching.